Good morning. We're going to try this again, some final exam review. Couple questions that we've had from the last test here, so the chapter 14 and 15 material, and then go back to some older stuff because we're going to go over stuff that we did a long time ago. Try to remember how polar and parametric worked and that sort of thing. So I got a couple of problems picked out from chapter 10, and we got the vector stuff in between there. Final exam is just going to be like one big list of questions. I think there's 14 questions or something like that. So they're more or less in book order. So the parametric and polar stuff, and then the vector stuff, and then the multivariable functions of 2 or 3 variables, partial derivatives, and double and triple integrals at the end. Let me start with test questions here because that's fresh on everybody's mind, and there was a couple of those I wanted to go ahead and work through, make some comments on before I go back. So let me get set up for that. Let's see if I can get this thing situated. So it's going to go over number 7 from the test, the max-min saddle point problem. There was quite a bit of pieces to that. I'll take a look at that one.
Sorry, 45. Yeah. Let's get up to 58 today.
Pretty good.
I can deal with that.
So we had this function.
I don't know.
Of 2 variables. Y squared minus 2y cosine x.
Oh, that would be drier.
And I said just to do this between negative x and 7. You get a cosine function in there, it's going to repeat. I mean, you'd get periodic stuff out of that. We just want to look at a bunch of them. So in between those 2 values, as far as we want to go at finding the critical points. So local max, min, and saddle points have to be critical points in there. So we want to find where the tangent plane is horizontal, which means partial with respect to x and partial with respect to y are both 0. And that's what we want to work through. And for the test problem, I had these written out already, what your partial derivatives are. Partial derivative with respect to x is 2y sine x. There's no x's in that term, so it would just come from your derivative of cosine being negative sine. If x is the only variable, and then if y is the only variable, you do have functions on both terms. That's 2y minus 2 cosine x. So that was written out, but those are the derivatives, first partial derivatives for that one, which is what we need to find. Critical points. So going on from there, we have to satisfy 2 things. Both of these have to be 0. 2y times sine x has to equal 0, and 2y minus 2 cosine x has to equal 0. This one, you got subtraction in there, so if you rearrange this thing, divide by 2, you get y equals cosine x. That has to be true. And this has to be 0, which actually breaks up into 2 possibilities. So this is a multiplication. So 0 factor property tells you either y is 0 or sine x is 0. But that's and y equals cosine x. So if y is 0 and y equals cosine x, that means cosine x is 0. So that happens when x is pi over 2 or 3 pi over 2. Those are the places on the unit circle where cosine is 0. Now, we're going from -1 to 7. That's a little bit farther than just from 0 to 2 pi, but it doesn't get out to any other places where cosine is 0. Cosine only has those 2 zeros in between that range, so those are the only ones that we want to do. Now those go with the fact that y is 0. So those are these ordered pairs. I'll start keeping track here. Pi over 2, comma 0, and 3 pi over 2, comma 0. And then this possibility, if sine x is 0 and y is cosine x, well, sine x is 0 means x is 0 or pi or 2 pi. Those are the ones between -1 and 7, the zeros of the sine function. And you're on y equals cosine x. So you'd have x is 0, cosine of 0 is 1, or x is pi, y is cosine of pi, which is -1, or x is 2 pi, cosine of 2 pi is +1 again. So you get a sense of what might be max min stuff here. That looks right for that one. And then analyzing each of those to be sure whether it's a saddle point or what is going on there. I don't know what the graph of this looks like, but we can do that using the D thing. So we'll use a big discriminant thing that helps to sort all of that.
Turn it off.
Okay. I got a little shadow here, but
Timothy just did.
so we want to analyze each one of these things. We have to look at our second partials to do D, and what happens with that. So the capital D thing is supposed to be second derivative with respect to x, second derivative both with respect to y. Those are multiplied minus the mixed partial fxy or yx squared. So that's your mixed one. So writing those down, those were given on the problem, and they're not easy, they're not hard derivatives to calculate, but they were written down already. Just the type of problem this is, I did not want people to make a mistake taking a partial derivative and end up with some huge situation created from that early mistake that who knows what you're going to find for critical points then. So I designed the problem to kind of avoid that by writing down what the partials were already. So that saves a little risk there. The mixed partial is, oh, I'm sorry, this one's just 2. 2 sine x is the mixed partial, so this is 2 sine x squared. So this thing comes out to 4y cosine of x minus 4 sine squared x. And we want to evaluate that at each of the critical points to see how it comes out and run this test thing on what happens with this. So for instance, we could do this on the whole table. I'm not going to go through them all right now, but here's one of your critical points. At 3 pi over 2 comma 0, D is equal to 4 times 0 times cosine of 3 pi over 2, which is even extra 0, minus 4 sine of 3 pi over 2 squared. So that's 1. We get 0 minus 4 equals -4. Since D is less than 0 there, that's a saddle point. And so you have to go through and run the test on those. If D comes out positive, then you have to look back at the second partial, see if it's sort of concave up or concave down, and go by that normal. Concave up means local min, and concave down means local max stuff. All that applies if D is positive, but in this case, when D is negative, that means it's a twisty thing there. It's a saddle point. All right. The other one from the test that I wanted to cover now was number 3 from part 2. Had that written down to try to get to this one. Make a observation about this. So let me copy this problem down. We were looking at, it says change to a polar integral, then evaluate. So it's a double integral to start with. Well, it's a double integral. Starts off looking like pretty big ugly situation here, dx dy. So it starts off Cartesian or rectangular. We're going to change it to the equivalent polar equation and then evaluate. Now, some of that stuff looks polar-ish. When you have x squared plus y squared, you should kind of think about the distance from the origin, and that kind of looks like an r thing. It is. That's key observation on this thing is that e to the square root of x squared plus y squared does not have a nice antiderivative at all. So even if it didn't say change to polar, you're kind of stuck with this. If you try to integrate this with respect to x, you're not finding an antiderivative to that. I actually went to Wolfram Alpha to look this one up, and the integral of that with respect to x is 1/2 square root of pi e to the y squared times ERFI of x, which is the imaginary error function. So if you know what that is, good for you. I don't know what that is. Right? This is not one of the elementary functions at all. So that's a long way of saying there is no nice antiderivative to that thing at all. So in Cartesian, you're not going to be able to do that function. Changing to polar gives you a chance. It turns some functions that are impossible, that don't have a nice antiderivative, into a function that does have a nice antiderivative just in changing coordinate systems. That's part of the reason we do these alternate coordinate system. Let me get into that. So this is one of those cases where polar works out better. Now, polar conversions are this: x squared plus y squared equals r squared. So this thing is just positive. That's e to the r. That's going to be nice. The unit of area here going from a rectangle to a polar thing, instead of dx dy in polar, it's r dr d theta in polar. That's one of the things that helps this one come out nice. Or come out kind of an interesting antiderivative with that, but we do have that to worry about now. And then we got to think about what this region looks like to map this out in terms of r and theta instead of x and y. So we got to look back at this sketch on this, or the conversions and how they fit here. So this is an integral with respect to x. That means we're going from x equals 0 to x equals this thing. So on your sketch, x equals 0 is here. This is positive thing, some kind of function of y that we got out here. Well, let's see what that equation becomes. So I'm thinking about x equals square root of ln of 3 squared minus y squared turns into x squared. Now if I square both sides and then add the y squared, I get this. X squared plus y squared equals ln of 3 squared. Recognize this is a circle. X equals the square root of that is the positive side of that circle. So it's the semicircle out here is the function that I'm looking at. Radius is ln of 3. And so the region that we're looking at is between 0 and the semicircle. And then y, the outside integral, is going from 0 to ln of 3. So we're only looking at the positive part of this. From 0 up to ln of 3 on the y-axis, we're just looking at this region right here. That's our region, capital D, that we're looking at. So that's easy to do in polar. R is going from 0 to ln of 3, and theta is going from, well, we're just first quadrant here, so theta from 0 to pi over 2. So those things don't work with a nice conversion right here. We're not talking about the same variables. It really works off the sketch. You got to take this thing and sketch your region and see what that region looks like when you use polar coordinates on it. That's how you switch back and forth between those. And then it's r times e to the r that we have to integrate. You could do this theta first and then r because they're both just numbers up here. So they're not dependent on each other. We don't have to have one inside of the other. You could do it either way. But at some point, you have to integrate e to the r times r, which is a integration by parts thing. E to the r dr, I can do the antiderivative of, and u equals r, I can do the regular derivative of. So du equals 1 dr. And this thing will convert using, well, we're keeping the same variables. We're doing integration by parts. The inside one, still from 0 to ln of 3 because I'm still in r, but it's u times v, r e to the r minus integral v to u. So now my integral is just of e to the r dr. And this whole thing is inside the integral d theta. This isn't that hard to do. We're still going from 0 to ln 3. That one's already outside the integral. Antiderivative of e to the r is still e to the r. So, okay, a couple of calculation things to people off on this a little bit. But be careful substituting stuff in. Might not be as simple as you think. So let me go through it. That's ln of 3 times 3. That's e to the ln of 3, which comes out nice. That's good. Minus 0, e to the 0, which is just 0. Okay, that's what I got from that first term. This one, e to the ln of r, or e to the ln of 3, which is also 3, minus e to the 0. So this is 3 ln 3. That's 0. That's 3. That's a 1. So we get a different number in there. Now, there's a couple different versions of this test. You might have had 4s in there instead of 3s, but you got very similar stuff. We have to integrate that, but that's just a constant to integrate from 0 to pi over 2. So you end up with just pi over 2 times all of that in there. That part's easy. Not going to spend more time on that. All right. So those are ones off from the test to give a sense of what happens there. One of the reasons we study the other coordinate systems is there's things that are impossible to integrate that just don't have an antiderivative. And one of the techniques for figuring that out anyway is to change coordinate systems. Sometimes that makes it into a possible thing in that changeover. And double integrals are a useful tool for that. All right, going back, I want to cover some older stuff too. I had a few things marked out of the chapter 10 review, which is going all the way back to parametric and polar. And that was a long time ago. So I want to work through some stuff there, just kind of some examples of the type of stuff you'll see on the first part of the final. I think I did put them more or less in chapter order on the final. Not that you have to work them in that order, but you see some parametric and polar stuff, so we got to remember how this stuff works. So these did come from the book, but chapter 10 review, it'd be good to look at review questions from each of these chapters. Just not that you're going to work all of them, but work some of the basic ones from each of the chapter reviews or the equivalent things in Lumen. I mean, there's similar stuff there. But the chapter reviews in the textbook give you a summary. Now, they cover everything in those chapters, which we didn't do, but you have the topic list to go by. I'm going to do 4 and 14 and 37 from there. So starting with number 4, it says to sketch. Well, it says really to do two things, sketch and eliminate the parameter. To find the Cartesian equation of the curve. So, and this one's x equals 2 cosine theta, y equals 1 plus sine theta. Now, this is not a t, it's a theta, but we're still just looking at it parametrically here. X and Y are both functions of another variable, a parameter. And if we can eliminate that, we can get an equation just in X and Y. And we can draw a sketch of this thing. Doesn't specify certain values for this, but you got periodic functions. So if we go from 0 to 2 pi, we could just plot points and see where this curve wanders around. But I kind of think this sketch will be easier. We'll see what happens. We might be able to sketch it easier once we have a regular XY equation. So I'm actually going to do this first and then think about the sketch of it. I'm going to put that in terms of X and Y. You just have sines and cosines, but this is not the polar theta. It's just a parameter. So we're not using conversion stuff from polar. We're just talking about having a parameter in there and wanting to get rid of it, which means either solve for theta in one of these and substitute it in, or use some kind of identity. When you have sines and cosines, you should think about this. This is typical with these kind of problems, is that we're going to use this. Whatever the parameter is, sine squared plus cosine squared equals 1. All right, so I'm just going to use that and solve, not all the way for theta, but solve for sine and cosine. So sine theta is y minus 1. And cosine theta is x over 2. So when it says eliminate the parameter, it's not really a conversion from one coordinate system to another. It's just doing the algebra to eliminate that variable, in this case theta, and write it in terms of the other things. So substitutions allowed rearranging the equations, plugging things into known identities like that. Those are the tools that you have. If I plug these things in, I got x over 2 squared plus y minus 1 squared equals 1. That's looking a little bit more like a circle now. Not quite a circle because this division by 2. That's actually an ellipse right there because of the sort of stretched the x dimension on that thing. So this is going to go from plus or minus 2 on the x-axis. That's where you'd get 1, and y would be 0. So these 2 points. And then y, or not the x-axis, it's actually up at y equals 1. So it's 2 comma 1, negative 2 comma 1. The center of this ellipse is at 0, 1. And it goes 1 unit in each direction there. So when y is 0 or 2, this is going to be, when x is 0. So 0, 2 and 0, 1 are on there. You got no ellipse here. So conic sections practice there. But you could graph that. Now, if you just took these original equations and started plugging in some points from 0 to pi over 2, you'd get these different things. You know, when theta is pi, you could also do sketching this way. When theta is pi, x is 2 cosine of pi, which is negative 2. And y is 1 plus sine of pi, which is 0. So you'd get this point out of that. 1 plus cosine of pi is 1 plus 0. 1. Okay, I can. So you get these same points out of it at the different values of theta. You could get the coordinates out of it that way. But Cartesian form or XY equation, we're used to knowing what the graphs of those things are. We know a little bit more about it. Okay, so I sketched it and I eliminated the parameter. This is going to cover this entire thing. If you're at different values, you're going to get all of this. There's no domain issues with any of this. So theta is going to keep going forever, and we're just going to go around and around this whole curve. You have to be careful about that because the curve that you get when you eliminate the parameter, sometimes your parametric curve is just wandering around parts of it and never hits outside of it. But if you think about the ranges of these things, the x range is from -2 to 2. And the y range is from 0 to 2. It's going to cover all of the points on this ellipse this time. Calculator can do those. I mean, a calculator can do the sketch of that if you go over into parametric mode. So if you're taking your time working through a final, you could switch over to parametric mode and graph it just to kind of confirm those things. That's worth taking the time on. That's that problem. Said I was going to do 14 also. While we're in parametric, one of the other topics I mentioned was arc length. We did arc length in a couple of different forms along the way. We're only doing the parametric one here. And so the underlying formula for arc length, you can integrate to get arc length in parametric. Integrating with respect to t, that's usually the parameter is t. So you got some t values that you're going to and from out there, whatever a and b are. And the formula for arc length, those little right triangles in there. The hypotenuse is dx dt squared plus dy dt squared inside that big square root. So if you remember arc length integrals, they always start off as the integral of big square root of something. So most of them don't come out too nice, but most of them don't come out nice at all. But there's some selected problems in here that do come out to an integral that you can work out. And this one does. Number 14 is asking for the arc length of x equals 3t squared, y equals 2t cubed, 0 less than 2 less than t. So we're just going between when t is 0 and when t is 2. So it gave you the t values on that. We could think a little bit about the sketch on this one. It wouldn't hurt. You could eliminate the parameter here because you can solve for t and substitute. We're going to get kind of a weird power if we do that. But when t is 0, we get 0 at both of those, so we're at the origin. When t is 1, I'm going to go through 3, 2. And when t is 2, I'm going to be at x is 12 and y is 16. So we're going off into first quadrant here. X is positive and y is positive when t is positive. So we're just going from the origin, 3, 2, 12, 16, some kind of weird curve this way. And stopping at that point, those are our values then for t is just going from 0 to 2. This curve would just, the parametric curve would just go through this thing from 0, 1, 2. It's not backtracking or not anything weird. So we're going to get the right length if we just go from 0 to 2. I need my derivatives inside here then. So dx dt will be 6t to the first. That gets squared in here. And dy dt be 6t squared. Also gets squared in here. So simplify that out. So we got a 36t squared plus 36t to the fourth. You might think at this point, it looks like somebody doctored this problem to get that to come out nice. Not just the same number, but a nice perfect square. That's great. So the 36t squared can factor out and get a 6t on the outside. And when you factor that out, you get 1 plus t squared on the inside. That is positive t out there. Square root of t squared is absolute value of t, but we are talking about positive values of t anyway, fortunately. So that's nice there. That made it a nicer integral to deal with. Integral big square root of something, you either have to get a nice perfect square, or you have to get something where letting u equal the inside will work. Or you have to get one of your inverse trig forms. But in this case, the u substitution is going to work nice. So this is du equals 2t dt, and that does exist out here. That's 3 du then. So I would just have 3 du square root of u, and u is going from 1 to 5. So pretty straightforward integral from there. So I'm not going to spend time working that out, but you get the number out of that. It's definite integral. A positive number for the length of that thing. The other one I had marked here to do was number 14. I say I grabbed a different problem than what I said there. So if you're actually looking these up, this is not number 14. This is actually number 37. I jumped over 14 and went to 37. That's the arc length one. I do want to do number 14. So let me get back to that. Remembering how polar stuff works also. And that we've been using polar because we put that within our cylindrical and spherical systems. So that's not like the parametric stuff that we haven't seen in a long time. But number 14 is just asking to sketch the polar curve. And that was one of the topics I put down. It's just sketching one of these things. So a polar graphs, I called it in the topic list. We got to be able to graph these things in polar. This is, I don't know what this one is. Let's see. It's r equals 2 cosine theta over 2. So I could use some half angle thing or something, but I don't think that really makes anything nicer here. I'm just going to work with that. The technique to remember for solving, not solving, but sketching these things was we kind of just draw a Cartesian graph of what this thing looks like. And then we kind of move it over into polar coordinates. So I want to start with thinking about y equals 2 cosine of x over 2. I'm just going to graph this thing and see what the regular trig function looks like. And then we'll kind of take those coordinates and wrap them onto a polar axis down here where theta equals 0 to 2 pi goes around the polar form. But it's just regular trig graph here. So we got an amplitude of 2. We go up to 2 and down to -2 for y. It's cosine of x over 2. So the period is actually 2 pi over 1/2 is 4 pi. That's a horizontal stretch. So we're going to go all the way out to 4 pi to finish one complete cycle of the cosine graph, which starts at the top, comes back to the top. So we got things like 0, 2, pi 0, 2 pi -2, 3 pi 0, and 4 pi, we're back to 2. And those are the coordinates, sort of key points on this thing that are going to come over to the polar graph and be useful. Now, when this thing hits 0, the intercepts of this function, those are places where the polar graph gets to r equals 0. When we do r equals 2 cosine of theta over 2, the points where r is 0 is points where this polar curve comes back to the origin. So at pi, I know this thing has to get back to the origin. And at 3 pi, but that's kind of in the same place. So I think that's going to be redundant. We'll see what happens there. 0, 2, we're looking at when theta is 0, r is 2. So that's 2 units out here. And it works its way down from there to 0. By the time I get to pi, I'm all the way down to 0. So it starts at 2, works its way down to 0 here. It's got some values between pi over 2 and pi that are still positive, so it's kind of working its way in here, right? If I go to pi over 2, it's going to still be some positive amount, but then it's working its way down to 0 here. So it comes into 0 at that curve, something like that. And then it's negative, right? From that 0, it works its way through negative r values around to 2 pi -2. Now this is also theta equals 2 pi here. 2 pi comma -2 would mean this is your angle opposite direction 2 places, comes out to here. So when we're between pi and 2 pi, which is these two quadrants, the r values are all negative. We're going out from the origin out to a -2 out there. So this is looping back around and coming out here. That's 2 pi. -2 that we're at now. And then from there, comes back to 0 at the 3 pi. So we're between 2 pi and 3 pi, negative values again. So between there, 3 pi comma 0 would mean 1, 2, 3 pi. We're back to 0 at this point. And it's going up from negative values there. Working its way back down to 0 there. Let me see, halfway between 2 pi and 3 pi. I got some negative value there. I don't need the exact value of it, but that would be at 5 pi over 2. Negative value would be down here somewhere. So that's working its way down back to 0. And then from 0 back out to +2 at 4 pi, which is back out here again. So that's a fairly rough, ugly looking sketch of that thing. Just working off from those values. But that was the technique on that. Draw out your trig, its trig functions of theta generally. Draw that out as if it were y as a function of x. Turn those ordered pairs into polar ordered pairs and think about the little segments that you get between like maximum values and zeros of r. That kind of a curve. In between there, okay, so that's all the way back to chapter 10. I got a little more time here, so I might work something from in between. We did chapter 12 and 13 on the vector stuff, and then we did 14 and 15 on the functions of more than one variable. So let me go to chapter 12 review and see what from here is on this topic list for the final, because there's a lot of stuff here. We're not doing all of it. We're not going to spend time on all of it right now, but chapter 12 review, to page 880 and, well, 882 and 883, a bunch of review problems from chapter 12. Dot product and cross product and stuff are in here. So on the topic list, dot and cross product, angle between vectors. It really looks like the only two chapter 12 ones. So we want to know how these things work and how they interact with the angle between vectors. So parts of exercise number 4, I'm going to work some stuff. Dimensional vectors. Chapter 12, review number 4 is what I'm looking at. We got some given vectors here. A is I plus j minus 2k, or -2 in component form. B is 3i minus 2j plus k. I'm more comfortable with vectors written this way instead of having all the letters going around, so I'm writing them out. C is j minus 5k, so that's got a 0 in the first component, 1, -5. Those are our vector components then. And we're doing operations on them. We're doing dot products and cross products with them and stuff like that. They also have the projection and the component here, which is not on your topic list, but the angle between A and B. I want to get to that. So let me do C and D. We're looking at parts of this problem. C is asking for what is A dot B. I'm going to do D. So the dot product, you multiply the components and then add this stuff up. So this is 1, 1, negative 2, dot 3, negative 2, 1. And the dot product, recall that was just multiply the components and then add this stuff up. So 1 times 3 plus 1 times negative 2 plus negative 2 times 1. That's the actual products going on. And then you take the sum of these things. A1, B1, A2, B2, and A3, B3 if you wrote it out with the subscripts. But it's 3 plus negative 2 plus negative 2 comes out negative 1. The dot product is negative 1. If the dot product was 0, they would be perpendicular. If the dot product is negative 1, that'll give us something about the angle. We'll come back to that. The cross product is the vector product of these things. D is asking for what is A cross B. And that was the determinant thing kind of set that up for us. So we find that by doing this convenient setup with IJK columns here and the coordinates in here. So A cross B, that would be 1, 1, negative 2, and 3, negative 2, 1 is inside there. And so your I component, leave out the I column and row and do a little cross multiply thing down here, or determinant thing down here, 1 minus 4. And your J component is the opposite of, remember every other piece of this cross product deal is negative. So the J thing has an opposite sign on it. Leave out the J column and you got 1 times 1 minus negative 2 times 3. And then for the K, you leave out the K column and you got negative 2 minus 3. So this is negative 3. 1 minus negative 6 is 7. Negative 2 minus 3 is negative 5. What do these things mean? Well, that one comes out to a vector. That's the vector. That's a vector that's perpendicular to both A and B. So the A vector and B vector would sit in some plane, and this would be normal to that plane. It would be a normal vector to that plane. That was useful for some stuff. Just gonna talk about angle between these things. So for part K of this problem, it asks for angle between A and B. And so one of the other geometric things that we had with vectors here was that the dot product was AB cosine theta, or A dot B which I already calculated here, is equal to the magnitudes times cosine theta. I haven't worked out magnitudes on these yet, but I'm going to need to for this. I did already do the work for A dot B, and I got negative 1. The fact that that comes out negative means this cosine of theta is going to be a negative, which means we're a second quadrant angle. They're more than 90 degrees between them. But I need the magnitudes to work that out. So the magnitude of A, look back at your components here, the magnitude would be square root of 1 plus 1 plus 4, square root of 6. Magnitude of B would be the square root of 9 plus 4 plus 1, square root of 14. And I'm trying to find theta in this. So that's negative 1 over square root of 84 equals cosine theta. So the exact value of it would be whatever the inverse cosine of negative 1 over square root of 84 is. Right? That would be the angle between them. It does say to do this correct to the nearest degree here, so we could actually calculate that out if we're in the right mode on that. I'm in degree mode. I've been doing some trig on this thing. So if I'm in degree mode, I can just do the inverse cosine of this. It is a negative value. I could write it and I could rationalize the denominator or whatever. I don't need to if I'm going to just calculate this thing. Negative 1 over square root of 84. Anyway, inverse cosine, that's 96 degrees. So it is greater than a 90-degree angle. They're more than 90 degrees apart, which happens in 3 dimensions. 96 is to the nearest degree. So 96 degrees in between them. What happens when the dot product is negative? The magnitudes, of course, are always positive. So if you get a negative dot product, that means they're more than 90 degrees apart. If you get a 0 dot product, that means they're exactly 90 degrees apart. That was our perpendicular thing. One of the things that cross product was good for, it gave us a vector normal to both of those. So one of the things that we did with that was get the plane equation from there. If we had a point, these could be the values that go into the plane equation. That's not really part of this. What other topics do we have here? Not a ton with the vector stuff that I left on the topic list there, so I think we're pretty safe on those, keeping that to the basic stuff there. Knowing how to work dot and cross products, and then of course knowing what they mean sort of geometrically, what they're useful for. All right, I gotta get ready for the next one here. I'm gonna hope this is useful. Leave this video up, but be looking for questions as we go along. Now this exam, I'm trying to keep track of all of these now. I got different finals, but this one is scheduled for the 7th at 8 o'clock. So if we're looking at Thursday morning, quite a bit of time between now and then. Hopefully other classes are winding down for people. I need some time to review this thing in between now and then. Send me some questions if you run into stuff that you're not sure about. If you run into anything that you need some reminders of, I can put up some other videos or just answer questions with clips on email. Anyway, so let me know which topics you're having trouble with. I don't think there'll be any big surprises on the final topic list. Is pretty good explanation of what's going on there. Now, if next Thursday morning isn't good for you, if you got to be somewhere that morning, I have later on the 7th, and I have a couple of finals I'm doing on the 6th and other classes, so I can plug you into one of those other times if necessary. I'm trying to keep them sorted out. But if you need your exam to be at a different slot there, let me know. I got some other things available, so let me know between now and then. I think I've gotten averages out to people for the most part, but if I haven't, let me know. I can let you know how things are looking so far. And any questions you have, get them to me between now and then. I will have another announcement to go out. Maybe more than one, but I'll definitely send announcements on Monday again with updated stuff or suggestions. So I'll be in touch.
Yeah, I saw that too.